All right, this is Honors Algebra 2 and Pre-Calculus. We are doing 8.6 in Algebra 2. We're going to do a revisit of transformation of functions. This is the second video in this particular section. So recall that in 2.7, we learned ways to change equations of functions to transform the graphs of those functions. So this is a review of where the particular function we're looking at is the square root of x. What we learned in 2.7 are that inside changes are horizontal and backwards. So for instance, minus h will take you right h units. Essentially, if there's a minus h, it's right h units. If it's a plus h, it's left h units. We learned about adding a k or some number to the outside, that if you add a positive number, it moves the entire graph up k units, and if you put a negative number there, it's down k units. So again, the inside was backwards, left was positive, and right was negative, which feels weird. We learned that if you put a number in front of the entire thing, in front of the function, that you can, if there's a negative, you can flip it, right, over the x-axis, and if there's a number here that's not 1, it'll vertically stretch the graph. And we learned that if you put a number on the inside in sort of that same position, a negative would make the graph flip horizontally, meaning over the y-axis, and having a number here, instead of stretching as you would expect, is actually a shrink, right? So we're going to go ahead and walk through those again in a little bit of practice, and if you're having any trouble with the concept as we walk through it, you might want to go back and watch the 2.7 video. All right, so we're going to describe the transformations from the generic graph y equals the square root of x and identify the domain and the range. Okay, so here's what's happening, right? So let's do the first thing. Let's talk about the transformations. All right, so there are 4. So the transformations that are happening. Number 1 is this minus 3. So the first thing that's happening is the graph is going to slide right 3. The second thing that's happening are 2 things sort of at once, right? So 2/3, because it's unclear which one's the second and which one's the first. The negative is going to make this graph flip over the x-axis. It's going to, x-axis. It's going to make it flip up and down over the x-axis. And the 2 is going to give a vertical stretch by 2. The last thing that's happening is this plus 5. I'm going to slide the graph up 5. So we're going to walk through how that graph would happen in a sec. So that's the first thing. Those are the transformations. The second thing I was asked to do is find the domain and range. So let's go ahead and do that, and then we'll use all of that information combined to graph. So the domain of this thing is that the inside of the root has to be greater than or equal to 0. So x has to be greater than or equal to 3. My domain is just from 3 to infinity. The range is a little bit trickier. So for the range, and this is the first one we've had where the range is going to be a little bit tricky. You kind of have to logic your way through this. So for the range, here's the deal. This thing is going to be 0 or positive, just the actual physical root, right? Just this piece right here, the root is going to be 0 or positive. If this thing were 0, right? So if the root were to equal 0, then this would be a negative 2 times 0 plus 5, which would be a 5. If the root is some positive number, then this is going to be negative 2 times a positive number plus 5, which is going to be smaller than 5, because this is going to be some negative number plus 5. Meaning that the biggest that this thing is ever going to get is 5, because any other value of the root other than 0 is going to make the thing, is going to make the entire output smaller than 5. So the range here is going to be from negative infinity to 5, because 5 is what would happen if the root were 0. If the whole root were 0, I'd get a 5, right? Because this would be negative 2 times 0 plus 5. If I pick any other number in here, I'm going to get negative 2 times some positive number, which means a negative thing plus 5. So my range is that 5 is the biggest, and this thing could go down to negative infinity. Now, when we put these 2 things together, it's actually going to make a lot of sense when we graph this. So if we graph this, and I probably should have had a grid handy, but I don't at the moment, so we're just going to make it work, right? So if we graph this, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Great. Okay, doesn't have to be perfect. All right. So let's look at what a regular square root of x graph looks like. It's got the point 1, 1, or sorry, 0, 0, 1, 1, and 4, 2. That's all we need. So first thing that's going to happen is this thing moves right 3. So 1, 2, 3, right 3. Right 3, 1, 2, 3, right 3. Okay, so that's my right 3. Then I'm supposed to flip this thing over the x-axis. Okay, well that's going to mean that instead of being, so this one on the x-axis stays the same, but these will flip to being below the x-axis. So I flipped it, great. Now I'm supposed to make it twice as tall. Well, what that's going to mean is that I double the y values. Double of 0 is still 0. Double of 1 is now 2. Double of 2 is now 4, right? So it's a negative 4. So that's done. And then I'm going to take this entire graph, I guess in purple, and we're going to move up 5. So instead of being at 0, this is now here at 5. Instead of being at negative 2, this is now up at 3. Instead of being at negative 4, this is up at 1. And this is kind of what my graph's going to look like. So if we go back now and revisit my domain, you can see that the domain is definitely 3 to infinity. And if we go back and revisit my range for a sec, you can see that the range definitely is from 5 downward forever, right? And that checks out. So let's go ahead and put that in a calculator and just see that we're correct in how that worked out, right? So let's scroll up for a sec. If I put this in a calculator, I have a negative 2 square root of x minus 3, close the parentheses, plus a 5, and let's go ahead and graph it. And sure enough, that's the same, rough version of the graph I got. Obviously better because it's a calculator, but you get the gist. Cool. So let's go ahead and try it with a P3. So same idea. You're going to describe the transformations, identify the domain and range, and then graph, right? So you can pause me if you want to do it without me. So transformations, right? So my transformations, number 1, first thing that's going to happen is left 1, right? The second thing that's going to happen is a vertical stretch by 3. And the last thing that's going to happen is up 4. So once I know that, and to be clear, you don't have to do these steps in the exact order I gave you. Maybe you do the domain and range last, because maybe it's easier after you graph. But so there's my transformations. So for the domain, I know the inside of the root has to be greater than or equal to 0, so x has to be greater than or equal to negative 1. So when I write my domain, I'm going to write it parenthetically as negative 1 to infinity. Now for the range, and again, the range requires a little bit more logic, right? So when we look at this function, right, the easy way to figure this out is to pretend that this output is 0, right? Because it could be 0 or positive, right? That's what the root could be. So if the root is 0, right, then this would be 3 times 0 plus 4, which would be a 4. If the root is bigger than 0, then this is going to be 3 times a positive number plus 4, which is bigger than 4. What that means is that the range of this thing is 4 at the smallest, and it will get bigger if other numbers are plugged in, right? So the trick with these ranges is figuring out, hey, the smallest that root could be is 0. If the root's 0, what is the numerical value? Okay, if I picked other numbers, what would this come out, bigger or smaller than that value, okay? So now let's go ahead and put the pieces together and see if we can sketch a graph. Again, I should have had a grid ready, but I don't, so we're just here and we're going to deal with it. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, great. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Cool. All right, so the original square root of x would be 0, 0, 1, 1, and 4, 2, and that's really all I need to do this. So the first thing I'm going to do is go left 1. So let's go ahead and take, we'll use purple for this. We'll go left 1. Move everybody left 1. Okay, I did that. The next thing I'm going to do is vertically stretch by 3. So that means essentially multiply the y value by 3. Well, 0 times 3 is still 0. 1 times 3 would give me a 3, and 2 times 3 would give me a 6. So this has gotten a lot taller, right? And the last thing I'm going to do is move up 4. So instead of being at 0, this is going to be up at 4. Instead of being at 3, this is going to be up at 7. Instead of being at 6, this is going to be up at 10. And my graph is going to look something like this, right? And so if we look at the domain and the range, you can see that sure enough, my domain starts at -1. Sorry, I did a terrible job of drawing it. That's supposed to be a -1. So starts at -1 and goes over. I kind of accidentally shifted a little too far over when I put it up. And that my range starts up here at 4 and goes up, right? So that's my range. It starts at 4 and goes up. And we can confirm that if we go ahead and put it in the calculator just to double check that our logic holds. So we can go ahead and, I'm just going to type over so we can make that a 3. This will be an x plus 1 and then a plus 4 on the outside. And there's our graph, right? Cool. All right, so let's go ahead and do some slightly more complicated ones. Now, these are a little bit more tedious, right? Because what's frustrating is that 2 on the inside is going to be not the most fun in the world. So in order to do this one, and I can go back to the original slide, but essentially in order to do this one, you have to yank this 2 out and make this an x minus a 1/2. Okay, so what's going to happen here, right? And you can kind of see this if we go back up to here. You can see that what they're doing here is they're factoring out this b, right? And then you're only looking at the number that was there before it factored out the b. So what's going to happen is when we list our transformations, right, the first thing that happens to the x is this minus 1/2. So the first thing that's going to happen is we're going to go right 1/2. The second thing that's going to happen is this horizontal shrink, because it's, so horizontal shrink by 1/2, because it's 1 over whatever that number is, right? The third thing that's happening is a vertical stretch by 10, right? And then the last thing that's happening is this minus 3, so down 3. All right, so those are my transformations. The domain and range actually isn't any harder than it's been in the other problems. The only one that you're, like, I think the graphing is the hardest part of this one. So the domain is just that the inside of the function, and I'm going to use the boring original inside of the function, is greater than or equal to 0, so x is greater than or equal to 1/2. Okay. My range, same argument, it's just about the logic of the output of this even root, right? So, so I look at this and I say, hey, this thing right here, this output is either 0 or positive, right? So if that root is 0, then I get 10 times 0 minus 3, which is a -3. If the root is positive, right, because those are the two choices, it's either 0 or positive, I get 10 times a positive number minus 3, which is definitely bigger than -3. So it turns out that my range is values that are greater than or equal to -3, right? It's going to get bigger than -3 as we go, and I forgot to write my domain parenthetically down here as well, so that's fine. All right. Okay, so now let's go ahead and put the pieces together and graph, and admittedly, this is not super duper fun to graph with this many changes, but we're going to make it work. Again, I should have totally put a grid, but here we are, so I'm just going to go ahead and lean in. The stretch by 10 is going to be a lot in terms of making this graph very difficult to read, but it is what it is. Okay, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 2, 3, 4, 5, 1, 2, 3, 4, 5. All right. Cool. All right, so an original square root graph is 0, 0, 1, 1, and 4, 2. We're just going to use those 3 points, right? So the first thing that's going to happen is we're going to move right 1/2, which I'm going to do in green because I didn't use green up top. Okay, so right 1/2 is going to be here. Just move half over, right? Then I have to do a horizontal shrink by 1/2. Now what that means is you're cutting the x values in half. So that's extra not fun right now because it's already a decimal. But essentially you're cutting the distance between the green dot and the y-axis in half. So that's going to be here. Halfway between the green dot and the y-axis is here. Halfway between the green dot and the y-axis is about here, right? Super fun. Then I need to vertically stretch by 10. That means I'm going to make these red dots 10 times higher on the y-axis. So 10 times 0 is still 0, so that's fine, right? 10 times 1 is a 10. 10 times 2 is a 20, which I can't even fit on my graph, right? It's way up here, somewhere up there, right? And then I need to move everything down 3. So I'm going to take this and move down 3, take this dot and move down 3, and take this dot that is already way too high up and move down 3, and my graph is going to be like some crazy steep x squared that is kind of a nightmare. Now we can confirm that by graphing 10 square root of 2x minus 1, close the parentheses, and then it was down 3, and we can graph it, and we'll see that it's super duper steep. That's weird. Did I do a plus 3? Did I do something crazy? It should be down 3. Let's see what happens. Trace, let's do 1/2 and see what happens. Well, that's not right. Trace 0.5. There we go. It is down, sorry. So to be clear, and this graph didn't do a good job of showing it, right? Sometimes your graph is just too pixelated to show it. That's why I wanted to show. So see how that dot exists on the graph? If the graph didn't exist there, the dot wouldn't exist. So this graph does actually do this. It's just that my calculator is not doing a good job of showing it. So sometimes if you zoom in, you can see it better. So you can see that if I zoom in, that line does exist, right? So just be aware that that line does exist. Sometimes it's a limitation on your calculator. If you're panicked that you're wrong, because I was fairly certain that I was correct, I double checked that I didn't put a plus 3, because sometimes that's the mistake, is that you accidentally type it wrong. But here it was just a matter of the pixels on my calculator not being able to show that really, really steep line, because the line is approaching a vertical line as it gets close to that spot. All right, cool. Let's try one last example like this, and then we'll do our last video of this section. So same idea, you're going to describe all the transformations. So this one actually has 5, which is going to be tricky. So the first thing I'm going to do is factor that 3 out, so I have an x plus a 4/3. So transformation number 1 is going to be left 4/3, right? That's this one on the inside. Transformation number 2 is going to be a horizontal shrink by 1/3, right? Because this 3, right, it would be 1 over that number. And then this one's going to be 2 transformations in 1. So 3/4, because it doesn't matter which order you do them in. You're going to flip over the x-axis, right? That's what the negative's going to do. And then you're going to do a vertical stretch by 6. And again, I'm not going to make you do a ton of these by hand, but you should be aware of, the concept. And then the last thing I'm going to do is I'm going to slide this thing down 2, right? So let's go ahead and find the domain and the range, and then we'll put all these ugly pieces together to graph. So the domain's pretty straightforward, right? The domain is just the inside of the even root has to be greater than or equal to 0. So x is greater than or equal to -4/3. I'm probably going to write it parenthetically as -4/3 to infinity, right? And then the range, again, is about the logic. So this is a -6 times a square root minus a 2. So this root, right, this root right here is either 0 or positive, right? So if the root is 0, then I get -6 times 0 minus a 2, meaning I get a -2. If the root is positive, then I get -6 times some positive number minus a 2. Well, that has to be less than -2, because I have a -2 and it's getting more negative. So that means that my range has to be from -infinity to -2, because -2 is the highest numerical value, okay? So now we're going to put all the pieces together, and again, for the bajillionth time, I should have made a grid, but we're just going to get through this video without one. So I'm going to look at my domain and range, -2, okay, so, oh, I need to fix that. My range is at the highest a -2, so I need to make sure that my x-axis is a little bit higher than that, because we're going to end up with some stuff under here. Okay, 1, 2, 3, 4, 5. Cool. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh, I missed that. That one's 5. 5. 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is why you should totally have grids on your note paper before you do it. Okay, cool. So I put the original dots on, 0, 0, 1, 1, 4, 2. Okay, this is all going to be kind of approximate. I'm not going to absolutely, wreck myself on this. So let's use blue for this transformation, because I didn't use blue yet. All right, sorry for the quick interruption. Let's get back to where we were. So we plotted our generic square root of x. We're now going to go left 4/3, so that's a little bit more than 1, and that's accurate enough for our purposes here. So a little bit more than 1. Okay, so we went left. Done. Okay, now we need a horizontal shrink by 1/3. So remember, that's basically cutting the distance between the blue point and the x-axis in 1/3. So that'd be about here. This one is going to be so close it's basically not noticeable. And this one's going to be about here, right? So there's our horizontal shrink by 1/3, right? Now we need to flip over the x-axis. So anything above so on the x-axis will stay on the x-axis, above will become below, right? And that was supposed to be 2, and so that'll be 2 below, okay? And then a vertical stretch by 6 is going to mean that we multiply the y value by 6. So this y value is 0, it stays the same. This y value is -1, it will become a -6. And this y value was a -2, so it will become a -12. So there's that graph. And then the last thing after all of that craziness is I'm going to move down 2. So down 2, down 2, down 2. And this is this crazy, incredibly steep line that is actually a curve, but it's going to look like it's a line, like it's super duper steep, okay? So now if we go ahead and graph that real quick in our calculator, just to confirm, so we're going to go to our y equals, we'll type in a -6, the square root of 3x plus 4, close the parentheses, minus a 2, and then we graph. And there's our graph, and it sure enough, it conforms with what we were expecting right there. Now, it might look like it doesn't go high enough up, but again, I assure you, if you trace to this x value of -4/3, it's going to go up high enough. So if you were to hit trace and hit -4/3, you'll see that there actually is a graph there, that this should connect the dots. It's just not showing it because of pixel issues on your calculator and a bunch of other stuff, right? So remember, the calculator technology is basically from like the early 80s and hasn't drastically changed that much in roughly 35 years. So, so there's your graph. It does conform with what we have, and that is the end of this video.